Good day, everyone. We are Group 8 and today we will be presenting our report on fundamentals of structural geology. Structural geology is the study of three-dimensional distribution of rocks, units, and their deformation histories. It plays a crucial role in civil engineering as understanding the behavior and arrangement of rocks can help us design safer and more efficient structures. Essentially, the relationship between geological structures, rock behavior, and engineering works is fundamental to successful project planning and construction. In our presentation, we will cover four main topics. First is the introduction to structural geology, next is attitudes of beds, next is outcrops, and lastly is the geological maps. Through this presentation, we aim to show how structural geology is not just a theoretical subject, but a practical tool for engineers to understand the ground beneath their projects. Let's begin with the introduction to structural geology. So let us now talk the definition of structural geology. Structural geology is a branch of geology that focuses on the study of how rocks deform and the structures that are formed due to forces acting within Earth's crust. These forces, known as the stresses, cause rocks to bend, break, or shift, resulting in geological features such as folds, faults, joints, and fractures. By studying these structures, structural geology helps us understand the movement of tectonic plates, the formation of mountains, and occurrences of earthquakes. In simple terms, structural geology explains how and why rocks change their shape and position over time due to Earth's internal forces. Now, let us discuss the scope of structural geology. Structural geology covers the study of how rocks respond to stress and strains, which helps explain whether rocks bend, break, or flow under different conditions. It involves the identification and analysis of geological structures such as folds, faults, joints, and fractures, which serve as evidence of past and present tectonic activity. This field also helps in understanding major tectonic processes, including plate movement, mountain building, and crustal deformation. Structural geology has important applications in engineering, mining, petroleum exploration, and groundwater studies, where knowledge of rock stability and structure is essential. Additionally, it plays a vital role in assessing geological hazards such as earthquakes and landslides, helping reduce risk to people and infrastructures.
Structural geology is a study of the three-dimensional arrangement of rock and the forces that shape them. It focuses on features such as folds, faults, and fractures, which provide important information about how rocks behave under stress. Understanding this rock structure is crucial for civil engineers. It allows us to design safe tunnels, slopes, bridges, and dams. By analyzing geological structures, we can anticipate potential hazards such as landslide or unexpected groundwater flow, which helps prevent accidents and reduce construction costs. In essence, structural geology provides the foundations for safe, efficient, and sustainable engineering works.
In this slide, we will examine the vital link between geological structure, rock behavior, and engineering works, which serves as the foundation for safe construction. Essentially, the physical structure of a rock, including its fractures, layers, and mineral composition, directly determines its behavior, such as how much pressure it can withstand or how easily it might slide. As engineers, we must understand this relationship to accurately design foundations, stabilize slopes, and build underground structures that can support heavy loads without failing. By analyzing these geological factors beforehand, we can predict potential hazards and ensure that our engineering works remain stable and secure throughout their intended lifespan.
The strike of a rock bed is the direction of the line formed by the intersection of the horizontal plane with the inclined surface of the bed. It is measured as a compass direction and represents the orientation of the bed along its horizontal trace. The strike provides information about the bed's orientation in the horizontal plane but does not describe the steepness of the bed's slope. The dip of a rock bed is the angle at which the bed inclines downward from the horizontal, measured perpendicular to the strike. It also includes the direction of a maximum slope of the bed. The dip quantifies how steep the bed is tilted. A horizontal bed has a dip of 0 degrees, while a vertical bed has a dip of 90 degrees. The strike and the dip together fully describes the attitude of the bed, allowing geologists to visualize and interpret the three-dimensional geometry of rock layers.
So this slide explains the instrument used to measure the attitude of rock layers and why it is important in geology. Geologists use a Brunton or geologic compass to measure the strike and dip of beds. The compass is placed flat on a rock surface to get the strike and then rotated 90 degrees to measure the dip direction and dip angle. This measurement helps geologists understand how rocks were formed and deformed over time. Measuring the attitude of beds is important because it allows geologists to interpret folds and faults, reconstruct the geology history of an area, locate valuable resources such as minerals, oils, and gas, and assess ground stability for engineering and construction projects.
The orientation of rock beds defined by strike and dip plays a crucial role in engineering projects. It affects slope stability as beds dipping along a slope can trigger landslides, while beds dipping into a slope generally improves stability. Bed orientation also influences foundation strength, settlement, and the overall safety of structures. In tunnels and excavations, bedding planes may act as weak zones, potentially causing collapses or requiring additional support. Understanding bed orientation helps engineers design safer roads, dams, retaining walls, and other structure while reducing geological hazards and ensuring long-term stability.
This slide discusses outcrops. Outcrops are visible exposures of bedrock found at the Earth's surface. They can occur naturally, such as in cliffs, riverbanks, where erosion removes soil and reveals the rock beneath. Outcrops can also be artificial, like road cuts and quarries, which are created by human activities. Studying outcrops helps geologists observe rock layers directly and understand the geological history of an area.
By studying outcrops, engineers can interpret the properties of the rocks beneath the surface. They look at the rock type, layering, fractures, and structural features like folds and faults. This helps predict how the rock will behave under stress, which is crucial for planning engineering projects. Outcrops are very important in site investigations because they give us direct evidence of the geological conditions without needing to dig. By observing them, engineer can evaluate slope stability, foundation, condition, and potential hazards, ensuring that structures are safe and efficient.
Geological maps are important tools used to show the distribution of different rock types on Earth's surface. They also display structural features such as faults and folds, which help us understand how rocks have moved and deformed over time. These maps include essential elements like a legend, scale, and orientation to help users correctly interpret the information. Symbols such as strike and dip are used to show the direction and angle of rock layers. Overall, geological maps help engineers, geologists, and planners make informed decisions about construction, resource exploration, and hazard assessment. This slide is about reading and interpretation of geological maps. Geological maps help us understand what's happening beneath the Earth's surface. By reading the symbols, colors, and patterns shown on the map, we can identify different rock types, structures, and landforms. These details allows us to visualize subsurface conditions and understand the geological history of an area. Overall, proper interpretation of geological maps is important in fields like engineering, mining, and environmental planning.
Site selection is the process of choosing the most suitable location for a project based on geological, environmental, and engineering conditions. In civil engineering, this step is very important because the safety and durability of a structure depend on the ground it is built on. Engineers study geological maps to identify areas with strong and stable ground, such as solid rock or well compacted soil, which can properly support buildings, roads, and bridges. One major goal of site selection is to identify stable versus unstable ground. Unstable ground can shift, sink, or collapse over time, which may cause cracks or even failure of a structure. Engineers also avoid areas with geological hazards like fault lines, landslide-prone slopes, sinkholes, and weak or loose soils. Building in these areas increases the risk of damage during earthquakes, heavy rain, or long-term ground movement. Finally, site selection helps engineers choose locations with suitable foundation conditions. Good foundation conditions make construction safer, reduce repair costs, and ensure the structure lasts longer. By carefully selecting the right site, engineers protect lives, save money, and create strong and reliable infrastructure. Foundation design is the process of determining the type, size, and depth of a structure's foundation so that the load of a building can be safely transferred to the ground. In civil engineering, the foundation is one of the most important parts of a structure because it supports the entire weight of a building, including people, furniture, and equipment. Engineers use geological maps and soil data to understand the ground conditions before deciding on the foundation design. One key task in foundation design is determining the type and depth of a foundation. Shallow foundations may be used when the soil near the surface is strong, while deep foundations such as piles are needed when surface soils are weak. Engineers also assess the bearing capacity of rocks and soils to make sure the ground can support the structure without collapsing or sinking. Another important consideration is predicting settlement and differential movement. Settlement happens when the ground compresses under load, and uneven settlement can cause cracks and structural damage. By properly designing the foundation, engineers ensure stability, safety, and long-term performance of the structure.
These slides explain how the geological maps are used in slope stability and earthworks to evaluate the natural and man-made slope by analyzing the soil, rock, and groundwater conditions to ensure the long-term safety and performance, including the identifying slope failure risks such as the landslide and erosions, planning safe cut and fill operations, and designing support structure like retaining walls, embankments, and drainage systems. And this is important because it helps prevent accidents and structural failures to protect lives and properties and reduce constructions and maintenance costs, minimize environmental damage, and ensure safer and more reliable infrastructure throughout the project's life. These slides explain how the geological maps are used in the route planning for roads, railways, and pipelines. Geological maps help engineers choose safe and efficient route by showing the soil and rock type, fault zone, and other ground conditions that may cause the problem during the constructions and operations. They are used to avoid the hazardous areas such as the fault zones, milling clays, and high weathered or fractured rock, which can lead to the ground movement and settlement and also the structural damage. For the final slides explain how the geological maps support hazard assessment. The hazard assessment is the process of identifying and evaluating geological hazard such as the earthquake, landslide, and volcanic activity and flood-prone sediment using information from geological map. These maps helps the engineer locate the fault line, unstable slope, volcanic zone, and weak or loose ground that can be increased damage during the natural event. By understanding where this hazard likely to occur, planners can avoid high-risk areas and apply proper design and safety measures. In conclusions, geological maps play a critical role in reducing disaster risk and helping the engineer design safer, stronger, and more resilient infrastructure that can be better protect communities in the long term.